A vector value function is a function from a domain D to Rn that assigns to each point in the domain a vector in Rn. The fact that the codomain is a space of vectors is what makes this a vector value function. And if the domain is a subspace of R, so this we consider, for instance, a function from R to Rn, a function of only one variable, we say that the image of a vector value function is a curve. So we have that the image of R in Rn, so this function maps the set of real numbers in Rn, so the image will look in general like any image of the line, an image of the real numbers. So, for example, let's consider this function. This is a function that goes from the real numbers to R2. So the type of vectors that this function is going to assign to each number, to each real number, is going to be a vector in R2. So we can look how this curve looks like, how the image of R is going to be in R2. So in order to do that, we can construct a table that for each value of t is going to assign the value of x and the value of y. So let's put here the value of x that will depend on t and the value of y that will depend on t. And so we assign values that we would normally do with a function. So for instance, when t equals 0, what is the value of x? Well, we plug in here 2 times 0 is 0. We plug it in here, 0 squared is 0 plus 1 is 1. So the first point that we have here is going to be the point 0, 1. So we put here a pair of axes, the x-axis and the y-axis, and so we are going to mark in this pair of axes this point, the point 0, 1. So this is going to be value 0 of x and 1 of y. So let's say that our point is going to be here. This is going to be the first point of our function, 0, 1. Let's assign the value 1. Let's substitute in the first component. 2 times 1 is 2. Let's substitute in the second component. 1 squared is 1 plus 1, 2. So we have the point 2, 2. So this is the point that we are going to mark here. So this will be 1, 2, 1, 2. So the point 2, 2 will be a point like this. That will be the second point of our curve. And so we continue here assigning values. For instance, the value 2, we substitute in the first one. 2 times 2 is 4. We substitute in the second one. 2 squared is 4 plus 1 is 5. So 4, 5 will be our next value. 3, 4. And so here we're going to have 2, 3, 4, 5. So this is going to be the next point of our curve. And so we continue. 3, if we plug in 3, we see that we're going to get big numbers here outside of our window here. Let's pick one in the other side, for instance, minus 1. If I plug minus 1 in the first one, I obtain 2 times minus 1, which is minus 2. I plug minus 1 here, I obtain minus 1 squared is 1. 1 plus 1 is 2. And so our new point to plug will be minus 2, 2. So this then is going to be 1, will be like this. Well, we can keep plugging different points and we'll see that our curve has a shape more or less like this. Well, this is going to be then the curve, the image of this vector value function that we call it curve. Well, this is the way then to graph a vector value function. So we have here the graph given by Sage Math That is a tool that you should use to graph your functions, but you should also know how to graph them by hand, so you can identify what curves actually match to what equations. So if we have, instead of this curve, a curve like this, for instance, so you know that this curve could never be this one, because at 0, for instance, we have here the point 0, 2 point something, almost 3. So that's not the point that you obtained here. So when here is 0, the point that you obtained here is 1. So you know that couldn't be that. So these kind of things are the things that you could use in order to identify what curves have what graph. Something about notations. I mean, the notation for a vector can be any of the notations that we have been using for vectors. You can use the angle parenthesis instead of the regular parenthesis, or you can use the notation ij, where here will be the two components of the vectors. Okay, so once that we know what a vector value function is, essentially it's a function whose codomain is the space of vectors. So we can calculate the same kind of things that we know how to calculate for real functions. So for instance, limit. So we are going to define the limit of a vector value function as the limit of each of the components. And so, as each of the components is a real value function, so these are just the familiar limits that you know. So in order to calculate the limit of a vector value function, so you have to calculate the limit of a real function in the same ways, I mean, using all the rules for limits that you know from Calculus 1. In order to calculate the derivatives, again, the derivative is defined as the familiar limit of this quotient. Well, is the limit, since the limit is the limit of each of the components, so the derivative is going to be nothing but the derivative of each of the components of the vector. So when you have the vector value function, in order to calculate the derivative, you just calculate the derivative of each of the components of the function. And in the same way that for the real value functions, we are going to say that the function is differentiable if the derivative exists at every point of its domain. So other notations, we can just write the derivative of a function like this, with a regular notation of derivative, or we can put derivative with respect to t, since this is the only variable in this function, so these notations are equivalent. So let's calculate some limits and some derivatives of functions. So for instance, let's consider the function that we were graphing before, are t equals 2t, t squared plus 1. So if we want to calculate the limit of this function at any point, so for instance, the limit when t goes to, let's say, 2 of this function, so this is going to be just the limit of 2t, t squared plus 1, and this is when t goes to 2, and this is nothing but the limit of each of the components of this vector. So in this case will be the limit of 2t, which is just 2 times 2, which is 4, and the limit of t squared plus 1, that will be just 2 squared, which is 4 plus 1, which is 5. So in this case, we have that the limit of the vector value function when t approaches to 2 is the vector 4, 5. If we want to calculate the derivative of the function, well, the derivative of the function is going to be the derivative of each of the components of the vector. So the derivative of 2t is just 2, and the derivative of t squared plus 1 is 2t. So this is the derivative then of the vector value function. And of course, these derivatives can be as complicated are the components here, but you know all the possible rules of calculation of derivatives from calculus 1, so all of them are going to be applied for calculating the derivatives of vector value functions. So in this way, we calculate the derivative for all values of t. Now, we want to calculate how much is the derivative at some particular value of the variable t, we just plug in. So if we want to know how much is the derivative at t equals 3, for instance, then the derivative is going to be 2, 2 times 3. So the derivative of 3 is 2, 6. How much could be the derivative at 5? So then will be 2 times 5 will be 10. So we have the derivative at any point that we may want. So in order to calculate derivatives that involve operations between the vectors, between the vector value functions, we can actually, for instance, if we have to calculate the derivative of this addition, we could actually just perform the addition and then calculate the derivative, or you can calculate the derivative by calculating each of the derivatives and then adding them. Well, you have the rules then here for all the possible operations. Here, if we have a number multiplied by a vector value function, we can take the number out and calculate just the derivative of the vector value function. If we have a dot product, we can calculate, as I said before, first the dot product and then calculate the derivative. Or we can apply the formula and calculate the derivative of the first one, and then do the dot product with the second one, and then do the first one dot product with the derivative of the second, and when we have these two vectors, then we add them. Okay, so let's, same thing with the cross product rule and the chain rule. So let's use the dot product as an example. Let's say that we have the functions, let's call u the function that we used to have before, that was 2t, t squared plus 1. And let's say that we have another function, b, that is also a vector value function, t, and the second component, let's say that is logarithm of t. And then let's say that we want to calculate the derivative of the dot product here. So we want to calculate the derivative respect to t of the dot product u times v. Okay, so we have two ways to do it. We can either do the dot product and then calculate the derivative, or we can apply the formula. Let's actually do it in both ways. So first, let's calculate the dot product of these two functions. So u times v, the dot product is, we have this and this. The dot product will be 2t times t, this is 2t squared, plus t squared plus 1 times logarithm of t. This is the dot product then of the two functions. We can expand this multiplication here to do the derivative easily. So this is 2t squared plus t squared logarithm of t plus logarithm of t. This is the dot product. And then let's calculate the derivative of this. So the derivative of the dot product is the derivative of this, right? So that would be the derivative of 2t squared will be 4t plus the derivative of t squared times logarithm of t. We apply the product rule, and then here will be t squared, the first one as it is, times the derivative of logarithm of t, which is 1 over t, plus the derivative of t squared, which is 2t, times the second one as it is, and plus the derivative of logarithm of t, which is 1 over t. So this is the derivative of the dot product. We can simplify here t squared times 1 over t. We can simplify this, and this will be equal to just t. And now here 4t plus t, this is just. So this is then the derivative of the dot product. But according with this property, we could also apply this formula that is very similar to the formula of the product of real value functions. So this formula said that first we should do the derivative of u. Let's start with that. The derivative of u, this is the function here, the derivative of u is going to be, the derivative of 2t is just 2, and the derivative of t squared plus 1 is 2t. And we are going to, this is the derivative of u, and we are going to also need the derivative of b. So the derivative of b is, according, b is this one, so the derivative of t is 1, and the derivative of logarithm of t is 1 over t. And now let's apply this formula, and so we're going to have that our derivative will equal to u prime, which is 2t, times b, dot product b. So b is this one, so here we are going to put t logarithm of t, and then plus this plus that is here, and then u, and u is this one here, so u is going to be 2t comma t squared plus 1 times b prime, and b prime is 1 comma 1 over t. Okay, so we have these two dot products and this addition. Let's do these dot products here. So this times this plus this times this, right? So that's the way to do the dot product. So in this case will be 2 times t will be 2t plus 2t logarithm of t. And now plus, and now let's do the dot product here. This times this plus this times this. Here will be 2t times 1 is 2t plus t squared plus 1 over t. Okay, so this is the result of the addition. Let's simplify what we can here, so that we have here 2t plus 2t, this is 4t plus 2t logarithm of t, and this part here will be t squared over t is t plus 1 over t. Now we put together here 4t and t, this is 5t plus 2t logarithm of t and plus 1 over t. So this result is exactly the same that we obtained in the other way. To calculate the integrals, now that we have the definition of derivatives for vector value functions, the integrals are defined in the usual way. An antiderivative of a vector value function r is defined to be another vector value function, such that when we do the derivative, meaning the derivative as we learned before, we obtain the original vector value function. And the indefinite integral of a vector value function is the antiderivative plus any constant vector. So be sure that this now is not a number like in the real value functions, but it's a vector. I mean, it's a constant vector, a vector that all the components are constants, do not depend on t, but are constants. And in practice, the integral of a vector value function is going to be the integral of each of its components. So for instance, let's calculate the integral of the function that we have been working with. So for instance, the integral or primitive of the function 2t t squared plus 1 dt is going to be the primitive of 2t, which is 2t squared over 2 plus a constant, comma, the primitive of t squared plus 1, which is t cubed over 3 plus the integral of 1, which is t, and plus a constant. So this is the derivative. So of course we can here take out these two, and will be just t squared plus a constant t cubed over 3 plus t plus a constant. Observe that the constant vector, if we want to write as plus c, where c is a constant vector. So this will be then equal to the function t squared, comma, t cubed over 3 plus t plus, and here the constant vector will be the vector AB. That would be another way to write this indefinite integral or this primitive. And in the same way, we can also calculate a definite integral. So the definite integral is just the indefinite integrals evaluated between A and B.